All right, this is AB and BC Calculus. We are doing Unit 4, Section 3, which is rates of change applied in contexts other than motion. So this is going to be a lot of word problems and talking about different ways that these word problems present. So good times. I know you love the word problems. So in recent years, like the last decade or so, the AP typically has some type of rate in, rate out free response problem. So in this section, we're going to look at several problems of this type and also some that just have a single rate. But let's look at some of the big ideas with these problems before we do that. So we're just, for this argument, going to use f of t for the rate in and g of t for the rate out. In the actual problems, it's often a different letter that's more relevant to the problem, right? Like if it's water coming in, it might be w of t or v of t for volume or something. Who knows? Anyway, so the rate of change of the thing, whether it's line of people, volume of liquid, number of apples in a display at Acme, amount of snow on the road, etc., it doesn't matter what it is, the rate of change of the thing is the rate in minus the rate out, right? The rate that the water is going into the bucket minus the rate that it's leaking out of the bucket. The rate that people are getting in line minus the rate of people that people are exiting to get onto the ride. The rate that the rate that rain is falling versus minus the rate that it's draining down the drains, right? So it's rate in minus rate out. It doesn't matter whether it's people or apples or snow or puppies. It doesn't matter what it is, okay? So in this case, that would be f of t, the rate in, minus g of t, the rate out. If that total rate of change is greater than 0, meaning the rate in is bigger than the rate out, then the line or the cup or the pile of apples or the snow is getting bigger. Like the line's getting longer, the cup's getting fuller, the apple pile's gaining apples, the snow is accumulating. If the rate of change, meaning rate in minus rate out, is positive, then whatever the thing is, it's getting bigger, right? More of that thing. It's getting more of that quantity. If the rate of change is less than 0, meaning the rate out is bigger than the rate in, then the thing is decreasing. The line is getting shorter, the cup is emptying, the apples or pile is losing apples, the amount of snow on the road is melting, like it's getting to be less, right, etc. If the rate of change equals 0, meaning that f of t, rate in, equals g of t, rate out, then the thing is staying the same. The line isn't changing. The cup is staying the same amount of volume. It's sort of an equilibrium where the rate in and rate out are the same. No apples are leaving or being added. There is no change in the snow on the road. It doesn't matter what these word problems are. I could make up gibberish words. It's the same concepts. So generally speaking, the thing, whether it's the line, the volume, the apple pile, the snow pile, whatever, is the largest or smallest at the instant when the rate in is the same as the rate out. So largest or smallest is going to depend on the context of the problem. But think about it this way. If the rate in is bigger than the rate out, then the thing is getting bigger. If and then the rate in and out are equal, nothing's changing, and then the rate in is smaller than the rate out, well, now the thing is getting smaller. So meaning that at that brief moment when the two values were equal, in was equal to out, that was the largest moment for this quantity, whatever it is. If you do it in the reverse, if the rate in was smaller and then became larger, then you were looking at something where it was the smallest. So again, these are big sort of overarching ideas about this concept. We're going to do a bunch of problems like this, but it's very likely you will see an AP free response that touches on these concepts. So let's look at example 1. You have a leaky bucket. Inexplicably, rather than replace it or fix it, you've just decided that that's your bucket and you're going to make it work as is. So you spend about 30 seconds trying to fill the bucket. Let t equal 0 be the time you start filling. You are dumping water into the bucket at a rate of y of t equals 3 sine of t over 2 in ounces per second, while water is simultaneously leaking out of the bucket at a rate of L of t, where that equals 5 minus 0.005 times the quantity t minus 5 pi all squared, also in ounces per second. So you're going to write a function for v prime of t, which is the rate of change of the volume in the water in the bucket at time t. So you can always use the AP notation. In fact, you should lean into the notation. So v prime of t should be the rate in, which is y of t, how fast you're putting water in, minus the rate out, which is L of t. That's a great answer. If I were you, I would make that the answer. I wouldn't bother to write the actual functions, right? You can write the actual functions, but keep in mind that you run the risk of miscopying something, and if you accidentally miscopy something, you could lose credit. Since they called them L of t and y of t, you can call them that. Please don't invent names for your functions, but if they are already named something in the problem, it's not wrong to write that name again. So this is the better answer. After 5 pi seconds of working, is the water in the bucket increasing or decreasing, right? Is the volume increasing or decreasing essentially, right? So there's a couple different ways to think about this. Probably the easiest way is to honestly just find what y of 5 pi is and what L of 5 pi is and see if one is larger than the other, right? Or you could do it as v prime of 5 pi, and then just see if it comes out positive or negative. Any of those is fine, right? So that's going to be y of 5 pi minus L of 5 pi. So let's go ahead and find what those values are. So y of 5 pi is going to be 3 plus sine of 5 pi over 2. Now, if this is a calculator section, you can make your calculator find both of these values, but I'm going to assume it's not since these are fairly friendly questions. And then I have a 5 minus what seems to come out to be a bunch of 0, right? Because when I plug the 5 pi in, the t minus 5 pi squared is going to be 0. So, seems to me that I get a 3 plus 1, because if you're having trouble, remember where 5 pi over 2 is. This is single pi over 2, right? 5 pi over 2 is one more lap around the circle. So I get 4 minus a 5. So 4 minus 5 is a negative 1. So the answer is that the level, or the amount of water in the bucket is decreasing, right? So the amount of water is decreasing, right? And then there's a couple different ways to justify it, okay? So you could say something like, because v prime of 5 pi is less than 0. That would be great, right? Or you could say something like, because L of 5 pi, which is the rate out, is bigger than Y of 5 pi, which is the rate in. Any of those, anything akin to that. So something like that. Like you don't have to have both. You could, so essentially you have to explain that you used the time at 5 pi and that it was a matter of whether the rate in or rate out was larger, essentially. All right, so you're going to try P1 without me. Feel free to pause me if you need to. So Fletch is stacking tiny pumpkins in a red wagon at a local farm. Mommy is removing the pumpkins from the wagon and putting them in a stack on the ground. It's not their wagon, but you explain that to a toddler. Fletch is putting the pumpkins in the wagon at a rate of f of t in pumpkins per minute, which is given in this equation right here. Mommy is removing the pumpkins from the wagon at a rate of m of t, which is given right there, also in pumpkins per minute. So write a function for w prime of t, the rate of change of the number of pumpkins in, it's not a bucket, in the wagon, but you get the gist, in the wagon at time t, right? So w prime of t is going to be the rate that they're being put in, which is f of t, minus the rate that they're going to be put out. That's the best answer. If you want to write the entire functions, you can, but you run the risk of doing something silly, right? So only write the functions if there's no other option. Like if they only gave you the rate, if they didn't call it f of t, if they just said 0.2 times the absolute value of t minus 10, then you'd have to write it. But if you're given a name for that function, please just use the name that was given. All right. Find w prime of 5 and explain the meaning in the context of this problem. So w prime of 5 is going to be f of 5 minus m of 5, right? Well, f of 5 is going to be a 0.2 times a positive 5, right? Because it would be negative 5 inside an absolute value, but that's, so this is the rate in, right? So this is the rate in, right? Minus m of 5, right? Is going to be, when I plug a 5 in here, and it might be worth you separately finding these two, right? F of 5 was 0.2 times 5, which is a 1 pumpkin per minute, right? And m of 5, oh, I need some more room. Sorry, folks. So m of 5, if I find this down here, I'm going to be a little lazy. M of 5 is going to be a negative, and it's up to you. You can leave it as a 0.01. You can treat it as a 1/100th. This is going to be 5 minus 15, right, which is negative 10 squared. So that's 100. So it's actually not as bad as you might think the math is, right? Plus 2.25. So negative 1/100th times 100 is a negative 1 plus 2.25. That's a 1.25. So 1.25 is my rate that I'm removing them, right? Rate out. And again, that's in pumpkins per minute. So w prime of 5 is going to be a negative 0.25 pumpkins per minute, right? So after 5 minutes, if you're asked to explain the concept, or the context rather, after 5 minutes, essentially Fletcher is adding 1 pumpkin per minute. Mommy is removing, right? So mommy is removing 1.25 pumpkins per minute, right? So the wagon is losing about 0.25 pumpkins per minute, right? So essentially, poor Fletch, trying as hard as he might to add the pumpkins, is just not able to keep up with mommy at this juncture, and the wagon is losing pumpkins, not gaining pumpkins, right? So again, the wagon is losing pumpkins, not gaining pumpkins. All right, let's go ahead and keep going. All right, example 2. Bailey is a big dog. He can reach the counter, and he's found a stash of cookies. Bailey grabs the cookies from the counter and deposits them in a pile. Riker is a small dog. Unbeknownst to Bailey, Riker is removing the cookies from the pile and eating them. Bailey is adding cookies to a pile at a rate of B of t. Select values of B of t are provided in the table below. So that's Bailey's rate. He's adding cookies to the pile. Riker is removing and eating the cookies at a rate of R of t cookies per minute. So all of these rates are in cookies per minute. Let C of t be the number of cookies in the pile at time t. What is the meaning of C prime of t in the context of this problem, and include the correct units? So C prime of t, we're not asked to find an equation for it, we're just asked what C prime of t is. So C prime of t in cookies per minute is the rate of change of the number of cookies in the pile. Right? So it's the rate of change of the number of cookies in the pile. Meaning if C prime of t is positive, it means that Bailey is depositing cookies faster than Riker is eating cookies. If C prime of t is negative, it means that Riker is eating more cookies than Bailey is yanking off the counter. Either way, no cookies for the humans. Very sad day in the Hogan household. All right, so find C prime of 10 and explain the meaning in the context of this problem. So Bailey is adding 2 cookies to the pile at 10, right? Riker at time 10 is, let's see, eating 5 cookies, right, per minute, right? So C prime of 10 is going to be B of 10 minus R of 10, right, which is going to be a 2 from the table, right, minus a 5, which I just figured out, which is negative 3 cookies per minute, right? So when I explain this in words and explain the context, after 10 minutes, right, so 10 minutes in, the cookie pile is getting smaller, right, because Riker's eating more, at a rate of 3 cookies per minute, right? So it's getting smaller. So I covered the smaller, right, because the rate is negative 3. Right? So that's why it's getting smaller, right? So it's getting smaller, meaning that essentially every time Bailey delivers 2 cookies, Riker eats 5 cookies, and the net change at that moment, the rate of change, the net rate of change is 3 cookies per minute in the negative. All right, it's fall, and the leaves are falling. Your neighbor Florence is a bit obsessive about cleaning up the leaves on the sidewalk outside. Did I do the, what did I, oh, hey, that's P2, sorry. That's P2, my bad. Sorry. Leaves are falling at a rate of L of t leaves per day. Select values for L of t are given in the table below. Florence is sweeping up those leaves, probably while muttering curse words, at a rate of F of t, also in leaves per day. Let S of t be the number of leaves on the sidewalk at time t. What is the meaning of S prime of t in the context of this problem? Include the units in your explanation. Okay, so S prime of t. So S prime of t is going to be the rate the leaves are falling, right, L of t, minus the rate that Florence is sweeping them up, F of t, right? And it's in, so it's going to be in leaves per day. So S prime of t is the rate of change of the number of leaves on the sidewalk. So it's not the number, it's the rate at which it's changing. So what that means is that if L prime, that says sidewalk, I just ran out of room. So what that means is if S prime is positive, then the leaves are falling faster than Florence can sweep them, and her cursing will get epic. If S prime of t is negative, then Florence is sweeping the leaves faster than they are falling, and she feels like she's winning. Okay, so we're asked to find S prime of 6, and using the correct units, explain the meaning. So S prime of 6 is going to be L of 6 minus F of 6, right? Well, L of 6 is 37, right? F of 6, right? If you need to find it, you can do it in your head or you can find it here. Well, that's going to be a 5 times a 4 plus a 10. Oh, Florence is going to be mad. That's a 30. So 7 leaves per day. All right, so S prime of 6 is 7 leaves per day, which means on day 6, Florence is very mad because the leaf pile, right, the leaf pile on the sidewalk is increasing at a rate of 7 leaves per day, right? So she's losing by 7 leaves per day, and she is mad, just in case you don't know Florence. All right, cool. All right, moving on. All right, it's a pandemic. People are getting in line outside Aldi, which opens at 9 a.m. We're going to call that T is 0. People are being let into the store at a rate of 20 people per hour. People are joining the line at a rate of J of T in people per hour. J of T is graphed here. Very poorly. I tried to make dots to show you points that I wanted you to notice. So is the line getting shorter or longer at noon? Justify your answer. Okay, so the length of the line, right? So the rate of change of the line, right, is going to be rate in, which in this case is J of T, minus the rate out, which in this case is 20 people per hour, right? So essentially, if J of T is greater than 20, so if J of T is equal to 20, the line's not changing, right? So basically, if J of T equals 20, the length is staying the same. Right, so however long the line is, that's how long it's going to stay. If the rate in is bigger than the rate out, then the line gets longer, right? And if the rate in is smaller than the rate out, then the line is shrinking, right? So the easiest way to do this is we look at this graph. J of T is in blue. Here's the rate out. Right? The rate out, the rate that people are leaving the line is 20. So if the blue line is on top of the red line, then the line is getting longer. So since 9 a.m. is 0, right? That's 9 a.m. 3 is noon. So if you look at noon, so at noon, J of 3 is 30, right? So since 30 is greater than 20, right, the line's getting longer, right? Because there are 30 people joining the line and only 20 people admitted into the store. So the line just got longer by 10 people in that instant, okay? What is the time when the line is the longest? Well, one of the things we discussed at the start of this problem was that basically when the two of them are equal, you can see in this entire window, the line is growing because the blue line is on top. At this moment, which would be 7 hours after opening, right? So that would be 4 p.m., right? At 4 p.m., that's the moment when the two are equal, right? So the line stays the same length, the same number of people arrive and get admitted. And then in this window, the line's getting shorter, right? Because there are more people being let in than are arriving, so the line is getting shorter. So the answer is T equals 7, which would be 4 p.m., because J of T was greater than 20 for values before 7. J of 7 is equal to 20, and J of T is less than 20 for values greater than 7, right? So the longest moment in the line will be when T equals 7. All right, let's go ahead and do a P3. You have decided to join in a huge team effort to build the world's largest snowball. You and your team are packing snow onto the snowball at a rate of S of T in cups per minute. At the same time, the snowball is melting at a rate of 4 cups per minute. S of T is graphed below. Time is measured since the moment you joined the team. You spend about an hour doing this, and then you decide you're over it. That's kind of the gist of this. All right, so is the snowball getting bigger or smaller after you've been doing this for 20 minutes? So here's 20 minutes, right? This is 20 minutes. Now remember, 4 cups per minute. Let's do a different color for this. 4 cups per minute is how fast this thing is melting, right? So this, right, this is the melt rate, right? This is rate out. It's melting at a rate of 4 cups per minute. So at 20 minutes in, you are packing snow on at a rate of 8 cups per minute, and only 4 cups per minute are melting, right? So The answer is that it's getting bigger, right? Because S of 8 is, S of 20, my bad. S of 20 is 8, and 8 is bigger than 4, right? So like you're packing faster than what's being lost, right? So S of 20 is 8. 8 is bigger than 4. Essentially what we're saying is the rate in is bigger than the rate out, right? So it's getting bigger, and the reason it's getting bigger is because S of 20 is bigger than 4, right? That's your reasoning. In the hour that you're helping, when is the snowball the biggest, right? And you can just assume it keeps going. I kind of ran out of space, but assume that the red graph keeps going. It doesn't really matter to this problem. It's clearly not going to be increasing anytime soon. So same question we've seen before. This is the moment when they're equal. They're equal 40 minutes in, right? In this entire time, the snowball is getting bigger because the amount of snow you're putting on is bigger than the amount that's melting off. But then in this window, it's getting smaller. So the biggest that this thing is going to get is when t equals 40. So at t equals 40 minutes, right, because S of t is bigger than 4 for values before 40, S of t is equal to 4, S of 40 is equal to 4, and S of t is smaller than 4 for values after 40, okay, and that's why. All right, one last set of problems here. All right, so this is not a rate in, rate out, this is just a rate. People are standing in a rather lengthy line to pay Hogan for Spirit Fest. The number of people in the line at time t can be modeled by L of t, which I've given you here. Find L prime of 2 and explain the meaning with correct units in the context of this problem. Now you can either do this by hand, which is absolutely fine, or you can make your calculator do it. If you want to make your calculator do this, you'd put this in as y1 with the negative 0.05, and you'd do x to the 4th, right? And then you could do math 8, which is n derive y1 with respect to x at 2, right? And that'll give you L of 2, right? This will give you L prime of 2. I misspoke. It'll give you L prime of 2. I'm going to go ahead and do it by hand because it's not an awful problem. So L prime of t is going to be, when I drop the 4 down in front, that's going to be a negative 2t cubed plus 3t squared plus 2t plus 2. L prime of 2 is going to be a negative 2 times an 8 plus a 3 times a 4 plus a 4 plus a 2. It's a negative 16 and a 12. So negative 4 plus 2, that should be net 2, right? We are given that it is people, right, and minutes. So this is people per minute, right? So L prime of 2 is 2 people per minute. And the context is that after 2 minutes, the line is growing. Because remember, they're not talking at all about people leaving this line. This is just the line is growing. So this is only the rate people get in line. Is growing at a rate of 2 people per minute, right? Or actually, if you want to be safer, you can say people are joining the line, right? So people join the line at a rate of 2 people per minute. There is no rate out here. I could have given you a problem where we talk about how fast I'm taking receipts and sending people out of class. But in this instance, there's only the one rate, and that's all you have. Okay, last one, P4. You have a test on Animal Farm tomorrow. You forgot to read the book, and you're cramming your reading as quickly as you can. The number of pages you've read in t hours after starting is given by P of t. Find P prime of 1 and explain the meaning with correct units in the context of this problem. So again, if you want, you can find this on a calculator. You certainly could put it in a calculator. I'm not going to. I'm going to go ahead and find it by hand. But before I do that, I'm going to rewrite a couple of things. I don't want to do the chain rule on that t to the t plus 1 on the bottom, so I'm not going to. I'm sorry, I don't want to do the quotient rule. I'm just going to do the chain rule. It's up to you. You don't have to. But so p prime of t is going to be a 1/2 drops down in front, so that's going to be a 4t to the negative 1/2, which I'll deal with in a sec. This will be a negative 10 t plus 1 to the negative 2nd, and then the derivative of t plus 1 is just a 1 anyway, and then plus a 3. So I get that my p prime of t is 4 over root t minus 10 over the quantity t plus 1 squared plus a 3. And it's not going to be hard to find p prime of 1 then. Again, you could use a calculator. So 4 over root 1 is just a 4. This will be a 10 over a 2 squared, so that'll be a 10/4, right? And then plus 3. So I get 7 minus 10/4. So right? That's 28 fourths minus 10 fourths. So I'm going to get 18 fourths. So my p prime of 1 is either 18 fourths, or you can write it as 9 halves, or you can write it as 4.5. I don't care. Either way, it is measured in pages per hour. Pages per hour. Ooh, that's painful. I think I meant minutes. Oh, well. So, maybe not. Either way, you're a slow reader at this moment. Okay, because yikes, that would be a bad sign, right? We'll double check my math, but I think it's not great. Oh, sorry, it's an 80. That does make a difference. Whew. Sorry, 80. I thought that that made you a very, very slow reader. I wasn't trying to judge you people. That's a 40. That's a 40. That's not a 7. That's a 43. That makes a big difference. 160, 172, 172. That's nicer. Think we get a 162. What is that, an 81 over 2? That makes a lot more sense. So 40.5. That makes a lot more sense. Whew. Now that's a slightly more reasonable number of pages to read per hour. See? So that's why we look at problems and see if we did something silly. Mea culpa. Okay, so what does this mean? Well, this means after 1 hour, you are reading at a rate of 40.5 pages per hour. Right? And you can see why it was a red flag that I thought you were reading 4.5 pages per hour. So we should generally operate under the assumption, especially, okay, if it's a problem written by me, it could be something stupid like this, where I accidentally just gave you the wrong number. But on the AP, they didn't give you the wrong number. So if you get that you were only reading 4 pages in an hour, you should think, oh, hey, maybe I did something silly. Right? And I'll just double check that my math is right on the other thing, because sometimes it's not. What was that? 40 minus 10 fourths plus, I think it was a 3. Hey, there it is. All right, cool. So there you have it. That is Unit 4, Section 3.